All right, so I've been working on some research on optimizing password rule sets. So before we dive into a lot of the specifics and look at some information on how this was done, I want to dive into some basics just to level the playing field a little for those that are not too familiar with it. So when it comes to attacking passwords and password hashes, we use word list attacks, which are just basic information you can find on the internet. Anything that someone can think of to use in their password, common words, phrases, lyrics. And when we talk about rules or rule attacks, we mean the modifications that happen to those passwords. For example, we can change potato into that. I've chosen some local words to modify. So this is pretty straightforward. But when we start applying these to a lot of different passwords, the possibilities kind of increase exponentially the longer the password gets. The more creative people get, the more that increases. And the further the length goes up, that goes up exponentially as well. I've got this nice little graph showing that with the bits of entropy being on a power 2 logarithmic scale. So when it comes to attacking these passwords and password hashes, key space is kind of the king. Key space is every single possible combination that you can use or want to use. So for a PIN code, it could be 10 to the power of 4. It's 9,999 different attempts you have. And the more or larger your key space is, the more possibilities you have, the more computation you have to do. Therefore, it's just the less you have, the better. But when you reduce, you also risk losing your results, your cracks. And there's a lot of data in the wild. So now that we have some basics down, a little about me. So I studied computer science in Delft. I work as a red teamer. I have a company that I run. This is my first time running or writing CUDA code. So to those that are more familiar with CUDA and do it for a day job, you know who you are. I apologize in advance. These are some of the gems that I collect. So up there, this is an emerald zoomed in. This is a meteorite. These are 2 very small diamonds, of which this one is a raw one. And this is the raw emerald you see on the left. I included a cat, so I heard about the kitten rule, but I already had this in before then. So I am quite active within the HashMob community. I also keep an eye on a lot of the other communities, and you can also find me lurking in the Hashcat and Hashtopolis Discord. Every year, I try and participate in the different password cracking contests that appear, and just very technical and different in general. So that key space, right? We want to try and reduce it as much as possible. And when it comes to rules and all these modifications, the first few are pretty obvious. But there's a lot of rules and modifications out there that you can do. So it comes with a few challenges. So for word lists, it's what are the most common passwords? The result for this was or the answer for this we kind of came up with was hash.org and now hashmob.net, containing a lot of data breaches, which can be analyzed, sorted statistically on how frequent words occur, or how frequent passwords occur, and kind of ordering them from most frequent to least frequent. Makes sense. The issue with rules is that that's not quite possible. Rules can have different orders, they can do different things, so you can deduplicate in a few different ways, but it comes with a very significant computational cost. So there's a few different methods that we have, like debugging rules with Hashcat. You can use Liebenstein distances to calculate a base word and a plain text and kind of see what the differences are there. RuleChef is a new release by Sanashur Prime, which uses Markov chains to see which rules in sequence are most frequent after each other. Buka, flag, and 40 rules are an example of using like Liebenstein distances debug rules. For all the rules that I analyzed, you'll find that flags rules are completely missing. This is because he personally asked me to not include his rules in the statistics before he passed away in March. So unfortunately, I've honored his request and removed everything. So how do we optimize these rules? And can anyone guess how many rules are out there? I kind of spoiled it yesterday a little, but I wonder if anyone remembers how many, roughly. Any guesses? A little more than 64. It's about 40 million. That's the amount that I found kind of unique spread throughout the online web. 14 million. And a lot of that is in different orders, in different types. Some are generated, some are based on analytics, and in general, there's a lot of them. Not all quite as effective. We'll see more of that later. So my goal with this was to kind of keep the crack rate at the maximal level while trying to minimize the key space. So we'll look a little bit at set theory and on how we can apply it, and go forward, look at some of the challenges, how we optimize it, and finally look at the application and some of the results. Who here is familiar with set theory? Show of hands. Just a few. Who here has seen a Venn diagram before? A little more. So to those that are not familiar with Venn diagrams, they look like this. It's pretty simple. You've got hobbies like basketball, soccer, and softball. Alice loves baseball, soccer, and softball, and Carol loves soccer and swimming. And there's an overlap between these two. There's also some that are unique to each. So when we talk about set theory and optimizing, it's really about keeping and looking at which ones overlap, which ones don't overlap. And when we're applying this to rules, we really want to know which ones are unique on this end, unique on this end, and unique on that end, removing all of the overlap in between as much as possible. But we have a pretty simple example here with 3. When it comes to 4, we already have an issue that this one and that one doesn't overlap visually. And as you go on, it gets a little complex. So, challenge, there's a lot of data. When it comes to passwords and password rules, we're working with quite a bit of data. And trying to store that all raw in RAM, it doesn't work. So I took some of the best high-performing rules on this end, some of the HashMob dictionaries. If you wanted, you could take the HashMob medium, one rule to rule them still, which is the smallest one, and it would take, at 10 bytes average, doesn't really matter, 7 terabytes of RAM. It just doesn't really work. And if you want to analyze everything, because there's a lot, 43 million rules, it's a large number and takes about 2.5 petabytes of RAM. It doesn't work. So let's look at optimization. And this went through a few different stages, but the result I kind of ended up with is the best first search. You run all the rules with a base word list and a target data set, and you count the amount of cracks that each rule gets. So you kind of just keep guessing in a hashcat setting, like the debug method that I mentioned before, but a little faster. You then go through a loop, take the best performing rule, remove the passwords from the target set that you're targeting, and then recalculate everything. The first one you removed from the target set's now getting 0 cracks. And through this method, you're trying to kind of reduce this one, then this one, then this one, in order from most frequent to least frequent. You analyze them piece by piece. And this is why you do the pre-sorting. This is a chart demonstrating the 40 million different rules, sorted based on how frequently they match. So it's an exponential curve, and this is quite rough. But it's also good for us because it means that the first few rules we're going to get are going to be the most efficient to begin with in our first pass. So this is kind of a little bit of an illustration of how it could look. So you apply 3 rules, 3 modifications to 9 different words, 9 different passwords, and the first modification gets like 105 over here and then 100 over there, and you get a bunch of planes. You do the same for the second rule, the same for the third rule, and that's how you get a total. But this doesn't factor in the overlaps. So the best first search algorithm, it stores the best ones that we found. We then recalculate. So for this one, we already calculated the first rule and marked them out. So now we only have these 2 to go. We re-evaluate them, changing them down. We do the same for C. We store them, so these turn from red to blue. And then only these are left. So we recalculate this, 130, and we go down to this. So that's how the algorithm kind of plays out. And this allows for some optimizations on the speed, which brings things down, but not quite to the level that we'd like. So this is version 6 of the program that I ran on 36 million rules. And in theory, if you wanted to complete it, it would take about 11 years on this method. So there's still one optimization that we can do. And that's because we sorted them in a logarithmic curve. We have them sorted from most frequent to least frequent. And when we do the recalculation every single time, we hit a point where it's going to be below a certain threshold. The ones that we marked as complete are going to be done. We're going to re-evaluate. And at some point, based on the first pass that we did, we know that the ones are going to be below the threshold that we found. So we're going to have our next best one and know that everything below is going to be worse, since it's sorted. And this allows for a little bit extra of optimization, and it actually makes it feasible to run this algorithm in a reasonable time span. So the best I could kind of get on this algorithm with version 6 was 6 days of pre-computation, and then a few days of computation, which resulted in about 100,000 different rules. And after some reprogramming, I was able to fix a few bugs, get the performance up a little bit, rented a nice little rig to work with, and did it for version 7 with a much larger data set. So we went with HashMob large, comparing it against HashMob full, which means everything that occurs 4 times in 13,000 data breaches compared to every single data breach, so all 13,000. And this is something that is currently still running. It's still computing away, and we've got about 160,000 rules so far, so it's still going. Let's take a look at the application. So it's been in development for about a year. It started in November of 2024. It's had 7 versions. The first few were just CPU-based, extremely slow, just a few megahashes per second. I ran into a bug on a miscompile from NVCC, which took about 40 hours to fix. It was awful. Version 7 had a lot of refactored lines and some optimizations, which were good for its performance. So it's about 5K lines, and it's going live right after this talk. So people that are interested can take a look at the source code. So running it, I used the HashMob wordlist as basis, everything that occurs in at least 5 breaches, frequency optimized based on real data, so it's relevant and accurate. It includes have I been pwned, it's 13,000, quite significant. The idea of the rule optimization is to analyze as many as possible, so the more the merrier. And we compare that against a larger data set. Instead of 5, we take everything. The application is written in Golang with a CGO link to a C kernel for CUDA. Contains a rough little library, and it depends on the xxhash function, something that people can probably help optimize as well. The best first search algorithm, it looks something like this to those that are kind of interested in the code. Processing of the rules. Scoring, checking if it's better or worse. I'm just going to go through this really quickly because I realize that no one's going to really read this. So I have a little demo video, but I'm actually going to do a live demo or try a live demo right after. So it's a pretty rough curve. This is a over-optimization or an overfitting of Sosander's data set. He had about 200 million rules, I think, and using the program, able to reduce it down to about 1/4 of its total. And you can see it plotted out. You can see how it kind of hits that mark. Then another test was the merging of 2 different rules, so Buka 4000 and Sapphire version 1, looks like, merged together, and you can see how it merges, but also optimizes it to a point where it's able to hit a certain mark faster. These are both overfit, so these are not something you'd want to use in a real engagement or something in real data. It's more of a practical proof of concept. So this is what that curve looks like originally when we did the first pass, and this is what it looks like after. So this is the same chart. And you can see some very big optimizations happening on that end. Let's zoom in a little, because these are the rules that people actually use in real-world data. The first 1,000 rules or so seem to be the absolute most significant. People, when choosing a password, will choose a few modifications, and those are just the absolute most common. So for those that are somewhat familiar with reading these are the most common ones. So toggling the first character, uppercasing it, appending a 1. We have appending a 1, 2, 3. Those in corporate scenarios might recognize this one as well. Uppercasing the first and appending a dollar, appending an exclamation point, or uppercasing the first and appending an @ So some of you might notice there's some inconsistencies there in quality, and it's very quick to bias. It's very sensitive to its input data. But it doesn't change the inherent concept behind it, and it will factor and filter out the bad ones very quickly. So these are the ones specifically with T0, appending 1, 2, 3, 1, 2, 0, 1, 2, 8, 8, etc., etc. So how does it compare to some of the other rules that we have out there? So the under 50K one I don't have listed here, but at a small scale, you don't really notice any difference. But as we kind of go up in the size of the rule, we notice that the performance increases substantially. So the 75K version of this rule set beats out most 100K variants that we tested against. The 100K version, on the other hand, is able to kind of be on par with most other 200 to 300K sized rule sets. That's quite a significant improvement looking at it from an efficiency standpoint. You'll get your results, your cracks, a lot faster. So this dataset is primarily meant to be used in a first attack scenario when you have zero information about the environment. These are a little bit more grained stats. So some of you might recognize some of the rules that you use frequently. On the right-hand side, we have quality, which is the hit rate, the amount of cracks divided by the key space multiplied by a large number just to make it readable. And you'll see that the 75K version here is almost twice as good, 7 times as good, 3 times as good. Nope. I almost got a butterfly in the laser. Yeah, and we see that the 50K version here with 67% cracked on the dataset we're targeting here beats out most of these ones here, which are almost double in size. So I also looked at the rule sets that we kind of based this on. So there were 478 different rule sets that were analyzed and combined here. And these sheets I shared yesterday as well. So you can look at them in your own free time, but you can kind of see where they originate from and what percentage was used. So OMG barbecue from, yeah. So there are some caveats to this method. It's basically just a very fast counter. It takes time, and there are optimizations that still can be had. So I'm also looking towards the community to kind of help with optimizing it further. It doesn't generate any new rules. It just takes the 400 different rule sets, combines them, and chooses which one it likes most. It stands on the shoulders of years of research. And it's an expensive compute. There's quite a bit of graphics cards being burned here. The pros, you can draw some interesting charts. It's fun. You can draw some fun things comparing different rule sets to each other, looking at how they crack things over time, because not every rule set will follow a perfect curve as I kind of optimized for. You can optimize rules, you can score rules, you can use statistics to help draw and find patterns, and you can use this in a corporate environment to really reduce the amount of rules you're using down to what works within your system. One practical example you can take is that when you're doing red teams, you are not allowed to keep all the passwords on hand when you're cracking them. But by doing this, you can reduce the passwords down to a rule set, essentially embedding the concept behind those passwords into rules, store those, and those are not in any way related to the company or the data, but they are a match to your word list that you're using in your engagements and the rule set that you now have. And you can kind of build that out further. So, in conclusion, we have some form of optimal word list, kind of based on statistical data, and now we can combine that with a new optimal rule set, kind of based on the most common modifications, based on statistical analysis of those rule sets. Some credits to the people that have helped me on this. Adam Lack has been a huge help in providing hardware for me to work with because I was low on RAM for some reason. Penguin Keeper for making the rule analytics that you can see over here, and Cake for providing the Docker containers that I've been using intensely with Vast.ai for the GPUs, as well as every single author that kind of helped make this possible. the whole list of rules that I used, the frequency that it occurs in, and percentage of it that remains, will all be kind of public and available. So thank you, and I'll try and do a little demo after as well.